In this video, I would like to discuss using a relationship known as the law of sines to solve a triangle. From geometry, you may recall that solving a triangle means finding all the side lengths and angle measures of the given triangle. Now, we've been solving some right triangles using sine, cosine, and tangent and other identities in trigonometry, but I also want to point out through the law of sines and through the law of cosines that trigonometry can help us solve non-right triangles as well. To show part of the proof of the law of sines, I would like to imagine a non-right triangle as shown below. And I'm going to drop a perpendicular line here, and we'll call this h for height. Now we could observe a couple of things about the triangles I have just created. First, sine of angle A is opposite over hypotenuse, so it would be h over b. Second, sine of angle B would be opposite over hypotenuse from the perspective of angle B, so it would be h over a. If I multiply the first relationship by b, I have b sine of a equals h. And I multiply the second relationship by a, I have a sine of b equals h. So these are both equal to h, which means they must be equal to each other. b sine of a equals a sine of b. And if I take both of these sides of the equation and divide by AB, I get the following relationship. Sine of A over little a equals sine of B over little b, where little a is the leg opposite angle A and little b is the leg opposite angle B. You could also show this from a different perspective, different perpendicular, that sine of A over A equals sine C over C. I'm not showing that part of the proof, but it helps us arrive at the law of sines. The law of sines states that these three ratios are equal to each other in a non-right triangle. Sine of A over A equals sine B over B equals sine C over C. And we can use any two of these three ratios and the equality between them to help us solve certain triangles. In particular, the law of sines is helpful where we know the following information about our triangles. Two angles and the included side, you might call that an ASA or angle side angle triangle. Two angles and an opposite side, we call that AAS. And some cases where we know two sides and an opposite angle, SSA. It turns out that this third category is sometimes ambiguous with the law of sines. It doesn't always lead to a unique solution, and so I'm going to overlook this third category for the purpose of this video. Here's an example of solving a triangle using the law of sines. So we have the following triangle given to us, and I'm going to take the time to label this triangle. I'll call this angle A, angle B, angle C. It doesn't really matter what my labels are, as long as my side lengths are consistent with that. So this side length of 10 is equivalent to little a, and we're trying to solve for little c and little b in addition to angle B. To solve for angle B, I will use the fact that the sum of the angles is 180 degrees. So we can say that B equals 180 degrees minus the measure of the other two angles, minus 50 degrees, minus 30 degrees. So the result, B equals 100 degrees. So we've solved for our three angles, and now let's find the missing side lengths, little c and little b. To do this, we can set up a ratio. We can say sine of A over A, or sine of 50 degrees over 10 is equal to Say we want to solve for little c first. So we'll say sine of c over little c. Now I can multiply both sides of this equation by c, and I could say c times sine of 50 over 10 equals sine of 30 degrees. I can also keep manipulating this, maybe by multiplying by the reciprocal of sine 50 over 10. I can end up with the equation, the relationship, sine of 30 times 10 over sine of 50 is equal to little c. Now, for this example, I do need a graphing calculator because I can give an exact value for sine of 30, that's equal to 1/2. I cannot give an exact value for sine of 50 degrees. So I'm using a graphing calculator here to get my answer, making sure the angle is in degree format, and I'm ending up with little c is approximately 6.5. Now we could set up the same kind of equation to solve for little b. So I'll go back to the pair that we started with, sine of a over a, or sine of 50 over 10, and I could say that is equal to sine of angle b, which we now know is 100, over little b. Once again, through some multiplication and division, I end up with this equation for little b. b equals sine of 100 times 10 divided by sine of 50. Once again, I'm using a graphing calculator to get this value, and it is approximately equal to 12.9. So we've just solved the triangle. We provided the missing angle measure, and using the law of sines, we were then able to provide the missing side